You look like you're not at your office.
Well, no, I'm not. Yeah, not right now, not yet. I got to go in later today, and I mean there was this order that we're supposed to shelter in place or something. I guess. Not sure what that means in terms of working from our office or not, but um, we'll see.
Yeah.
I
My
might
sister
go
was
into
actually
my
just
office.
telling me about that.
What's that?
My sister was actually just telling me about that news. So I haven't looked
Yeah, we're
into
not
it
we're
yet.
not sure we're not sure how that affects Cedarville since right now we've kind of transitioned into a distance learning protocol. So it might be different for us. We're not sure, but
Yeah,
so I'll probably go in later today and get whatever materials I need.
that's a good idea.
But I'm just kind of holed up in my bedroom right now. So
Gotcha. Well, I do have a couple questions for you, if that's all right.
yeah,
Um, I've been working on the homework set due Wednesday, and for problem 8.3, number 8, it's the one with matching the different officials with the 5 different cars.
yeah.
The problem is significantly different than the others in that set, and I'm struggling a little bit with setting up the problems.
Did you
I was
watch?
able to create the array to describe the problem, and then I moved it all around and ended up with 3 subboards. But I don't know how to find the requested probabilities.
Okay, so wasn't that problem kind of like the one I did in the lecture?
Um, if I remember correctly, the had the similar problem description, but you changed a couple of the illegal pairings, and
Oh,
so the
okay.
board was actually different. And then I also don't. It's possible that you addressed it, but I don't remember it talking about the probabilities like this. I think it was phrased more similarly to some of the other problems.
Well, but probability isn't going to really be all that different. I mean, all you have to do is divide through by, uh, I mean, how many total pairings are there? Was there 5 officials and 5 cars?
Yes. So
So,
that would be the standard approach. But for instance, for part A, it says, what's the probability that the first official gets the Volvo? And so I'd somehow have to find the number of ways that that can happen, the desired number of ways. And I'm stuck on
mhm.
how to figure that out.
Well, but then that would just reduce the problem to one where there's like an X in that row in that column. So it would reduce the problem to a 4 by 4 case. So, so let me just kind of show you real quick.
Sure.
So let's see. How do I do this? Okay, so what do you have? It's like uh how many how many rows it's 5 rows and 5 columns, right?
Here, I can just hold up my array to the camera and hopefully you can see it if you
Well,
want.
do you want just so
But it's 5 by 5 is what the whole thing is. And then
okay, so
if
do you
you want, I can
have
give you
visuals
my
on
finished
labeling
board.
columns or what do you or are the cars on the rows or something?
I put the cars on the rows and the officials on the top. But if
Oh,
you want, I
so
can give you my finished sorted board so you don't have
okay,
to move
so
everything around.
official 1, official 2, official 3, official 4, official 5. And then how did you label the cars down columns at
I
least?
did what you did on in the lecture, ENTLV, just the first letter of each type of car.
T ENTLV.
Yes.
Okay, so what were the restrictions for official 1?
Official one couldn't have an E or an N.
Okay. Official 2.
Oh, I'm sorry. It won't really matter. I gave you, what did I, let's see. What in the world? Oh, okay. I gave you the ordering of my finished when I rearranged the array of the
Oh,
cards.
okay.
Sorry about that.
All
So
right.
it should be ELNTV.
ELNTV.
Yep.
ELNTV. Okay.
Okay.
So what were the restrictions on official one?
E and N are illegal.
E and N.
Hmm.
Official two.
T was illegal.
That's it.
Yep.
Okay. Three.
L and V.
Okay. Four.
L for official 4.
Just L.
Hmm.
Okay.
And then E and N for official 5 as well.
All right. Well, um, you know, I see basically a 4x4 board with official one, official five, or a 2x2 board,
Hmm.
official one and official five, and the Escort and the Nissan. Right.
Yeah. I set it up like the left, your rightmost square up
Okay.
here, if you can see that. Oh, wait, sorry.
Oh, wait,
Wrong way.
here.
That one is how I rearranged everything.
So you have the 2x2 and then a single square and then like a little L shape in the lower right.
Yeah.
Yeah, that makes sense. So what you basically did was this. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so you went this, right?
Hmm.
This is like official 1 and official 5, apparently. Yeah.
Yep.
And E and N.
Hmm.
And then you put this guy all by its lonesome right here,
Yep.
which is basically official 2. So this is T and official 2, right?
Hmm.
And then you had a little inverted L shape down here. Is that right?
Yes. Yes.
And so that was official 3 and official 4.
Hmm.
And uh oh, so that's just L and V. Okay.
Hmm.
All right. Got it.
So that's as far as
Uh
I was able to get on the problem.
oh, okay. Well, let's call these things, board 1, board 2, and board 3. Right? So board 3 is this stuff right here. Board 2 is just this single square, which is sort of stupid, right?
Hmm.
And then board 1 is this stuff right here. Yeah.
Okay.
Then you're going to need to find eventually probably the rook polynomials for the whole board, the rook polynomial for the whole board, right? The whole board, that's what we call B.
Right.
Let me just say that like B is equal to B1 union B2 union B3.
Okay.
But the rook polynomial for B is going to be the product of the rook polynomials for these, yeah?
Right. And because we'll probably need, I'm assuming we'll need to find the total number of matchings for the denominator of some of the probabilities.
Yeah,
And that
right.
part that process is the part that is similar to the other problems. So I feel like I'm pretty confident with how to do that part, but I don't know how to find the other quantities we need.
Okay, so tell me what the questions are.
Okay, so part A, there's two parts. Part A says, what is the probability if a feasible arrangement of cars is randomly chosen that the first official gets the Volvo?
Okay, so they're saying, okay, so they're basically asking you for the number of feasible assignments where the first of it, where the first official simply gets the Volvo. Is that
As
it?
the numerator?
Yeah.
Okay.
So you're going to have to count the number of feasible arrangements, period, right?
Which is what this process here is, right? That you were starting.
Yes. I mean, you're going to have to count the total number of feasible arrangements. Because did they just say what's the probability of or what's the number of feasible arrangements at some point? Or do they just say,
They just ask for the probability on both parts. There's a probability.
okay, so the probability that the guy got a Volvo. Yeah.
Yep.
Okay. Well, okay, so let's count these things. So what about, I mean, look, these boards are simple enough. I can almost keep it in my mind, right?
Sure.
So let's see. We have the square, the 2x2 square. We have the singular square, and we have the inverted L shape. Yeah.
Right.
So if we go over here, what is the root polynomial x b1?
That is, it's going to be 1 plus 4x. And then let's see here. So it's raised to 2x squared. Yeah. Oh, you just did it.
Yeah. And what's the root polynomial for Rx b2? That's really, really easy.
0 plus x.
Well, 1 plus,
Or sorry, 1 plus x.
yeah. Root polynomial for b3.
Is that 1 plus 3x?
Plus,
Can we fit 2 in there?
sure.
Because it's just that L shape. So once you, oh yeah, you're right. Okay.
X squared.
There's one way. Yeah. I
Yeah.
was not seeing that for a second.
Yeah. So, okay, so what's Rx of B? Okay, well, clearly it's going to be 1, right? Plus, okay, how many X is it going to be?
It's going to be product of, what was it? Product.
Right, it's going to be the product of these things, yeah? Here,
Right.
we can do.
Is it going to be
Sure.
8x?
Okay. And so we're going to go, so we just have to expand. Let's have this thing expand this thing. Expand 1 plus 4x plus 2x squared. Oh man, it looks like somebody's been doing this. The thing about Wolfram Alpha is it's a learning database, right? So, and if you have enough people actually query this thing, it'll put in here. This is a good indication that we're going in the right direction here. So it's 1 plus 8x plus 22x squared plus 25x cubed plus 12x squared. I'm writing it down. or 12x to the fourth, right?
Yeah.
Plus 2x to the fifth. Okay, so there's our rook polynomial. So let me share this other screen with you again. Yeah. All right. So what's the total number of allowable arrangements? So the number
So
of good arrangements or good assignments.
it's going to be
Number of good assignments. What is it? Well,
5 factorial.
yeah, 5 factorial minus
8.
8 times 4 factorial plus what
25 times 3 factorial.
well 22 times
Oh yeah, sorry. Got ahead of myself.
22 times 3 factorial minus, oh man, I'm running out of room. Minus 25 times minus 25 times 2 factorial plus 12 times 1 factorial minus 2, basically. Yeah.
Mm-hmm.
So there's the number of good assignments, but then what are we to do about the situation where, let's see, about the situation where we have what did you say? Official one.
Gets the Volvo.
Yeah. Now, so when they said the probability, they said like, suppose we select a random good assignment. Yeah. Is that what they're thinking of doing?
Yeah, it says if a feasible assignment of cars is chosen randomly, what's the probability that official one gets the Volvo?
Yeah, right. So the total number of feasible assignments is what we just computed down here, right?
Right.
That's the total number of feasible. And so among those, whatever that number is, and by the way, we could compute that fairly easily, right, if we really wanted to. Then our question is, well, okay, how many of them actually have official one getting the Volvo? Well, if official one gets the Volvo, all that does, if official one gets the Volvo, then what that does is it basically eliminates that column and that row.
Okay.
And then it just reduces the problem. Does that make sense?
Yeah. Because we know that's going to happen. So
Then we have a new board. Okay, let's call it, I don't know, let's call it B prime. B prime, which is, I mean, B2 didn't change at all, right? But B1 changed. B1's just a couple of squares now. Know what I mean?
mm-hmm.
So let's call that like B1 prime. And then we have B2. And then we have like B3 prime also, yeah?
Yes.
Okay. And it's easy to remember, like B1 prime and B3 prime, those are going to have the same root polynomial. Do you know what I'm saying?
Yeah.
Yeah, I mean, those are like the same. Those are basically the same. So let's go over here. Okay, what's the root polynomial of x b1 prime? Well, that's the same thing as the root polynomial for x b3 prime. And that board was just a couple of squares in a row, right?
Right.
So there's one way to place 0 rooks on that. How many ways are there to place 1 rook?
2.
Yeah, so there's 2 ways to place 1 rook. So each of those is just 1 plus 2x. And of course, the rook polynomial for B2 is just 1 plus x, right?
Right.
So then the rook polynomial for the new board, you know, where official 1 got the Volvo, it's just going to be the product of those guys. So it's going to be 1 plus x times 1 plus 2x times 1 plus 2x. So that's just 1 plus 2x quantity squared, right?
Mm-hmm.
So that's 1 plus x. And what happens here? 1 plus, if I square this 1 plus 2x out, it's going to be 1 plus 4x
Mm-hmm.
plus 4x squared. Okay. I mean, look, we don't need Wolfram Alpha to help us with this. We can just do it, right?
Yep.
So it's going to be 1 plus, okay, how many x? Well, 4x plus 1x is 5x. Okay, how many x squared is it going to be?
There's going to be a 4x squared and another 4x squared. So 8x squared?
Yeah. Okay. And finally, what are we going to have?
4x cubed.
Right. Okay. 1584. Okay, I think I can basically remember that.
Mm-hmm.
I think I can basically remember that. Okay, so let's see. 1584. So what's the number of special assignments is equal to, okay, this is special assignments where official 1, right? So that is like official 1 gets the Volvo, right?
Mm-hmm.
Is what?
You have a 4x4 board, right? So do we start with the 4 factorial?
Yeah.
By extension, this came up in another problem. What happens if it's not a square board? If it's like rectangular, which dimension do you go off of for that first term?
Well, you would just have to think, okay, how many options do I have? So if it's like, you know, I don't know. So if it's like 3 by 5, how many options do I have for where I could place a rook in the first row? If it was 3 rows by 5 columns.
Mm-hmm.
So here, let me draw a picture. So how many options do I have? So this is the 3 by 5 case, right?
Yep.
How many options do I have? So 3, and of course, oops, I lost control of my finger there for a minute. Okay. 3 by 5. How many options do I have where I could put a rook in the first row?
1.
No.
Oh, if they're all available, okay.
So I have 5 options for where I could put a rook there, right? And maybe I place the rook like right, I don't know, if I place the rook right here, that would eliminate this row and this column, yes?
Mm-hmm.
So then following that, how many options would I have for the next rook? The second row.
4.
Yeah.
So
And
then you'd have
suppose
3.
put it here. Well, that would eliminate this row and this column. And how
Right.
many options would I have left? This
3.
Yeah. So it's actually 5 times 4 times 3, right?
Okay.
So then it's right. Oh no, maybe I put the thing here or something. 5 times 4 times 3. So it's like 5 put 3. Yeah.
Mm-hmm.
Is essentially what's going on here. 5 put 3. Yeah. So so if the dimensions of rows and columns were the same, it would be like 5 put 5, which is really just 5 factorial. Yeah. Right.
Okay.
That would be the total number of ways to place those things in there. So that would kind of change the calculation slightly. but not all that much.
Okay.
But okay, so up here, 4 factorial minus, what was it, 5 times 3 factorial? Was that right? Was
Yes.
it 1584 or something?
Yes.
Plus 8 times 2 factorial minus 4 times 1 factorial. And apparently there's 0 ways to place, uh, you know, so what is this? This was the number of place, 5 is the number of ways to place 1 rook, 2 rooks, 3 rooks. Apparently there was no way to place 4 rooks on that board. What was the board again? It was this thing. The new board was this. Apparently there's no way to place 1, 2, 3, 4. 1, 2, 3, 4. There's no way to place more than 4 rooks. That's clear.
Mm-hmm.
Is that, wait a minute. So, but we're saying that there's not even a way to place
4.
4. Is that true? Huh. Oh yeah. Right, because if you place a rook, think about it for a second. If you place a rook in that first, like that 05 column,
Mm-hmm.
that's going to eliminate that entire column. And then I only have 2 rows left. Does that make
Right.
sense? If I were to place a rook in one of those positions in the first column, I only have 2 rows left. So the most number of rooks I'm going to be able to place is 3. Make sense?
Mm-hmm.
So that's why this count stops like 1 earlier than it normally does. So that's the number of special assignments. So whatever that number is, you would just divide by the other number, and that would be
Okay.
the probability.
That's part A then. Part B seems a little bit more complex because it says we'll have to alter the board.
Oh, okay. Well, what does it say?
So again, we're supposed to find a probability, and it's the probability that the second official or the fifth official get the Volvo.
Okay. Okay. So, but the same restrictions apply?
Yes. And it says, hint, model this constraint with an altered board.
Okay, so I'm gonna redraw the board right here. What were the officials once we in the board, so can you read down the left column again?
Yeah, for the final board,
Yeah.
the officials were on the columns, and they were 1, 5, 2, 3, 4.
And what were the cars?
E, N, T, L, V.
Yeah. And then we had this, right? We had this thing, we had this thing, and then we had this thing.
Right.
Is that right?
Yes.
Is that looking good? Okay. And now we want official 1 to go. Okay, so what is it?
Official 2 or official 5 get the Volvo.
Official 2. So we want 2V or 5V. Yeah.
Okay.
Well, I don't know. I mean, who cares about that hint? Like, so 2V or 5V. Well,
do we do what we just did, except do it twice and do one where
Yeah, I mean, that's
two gets
probably
the
the
V
easiest thing to do
and then add
because,
them together?
yeah, because you can't have both of these happen at the same time. You know what I'm saying?
Right.
I mean, either the one happens or the other happens, and you would just add the two things together. So, I don't know. So if official 5 gets the Volvo, then this would happen, right?
Mm-hmm.
Okay. So look at that. I mean, isn't that going to be the same doggone board that we just did? I mean, look at it.
You're right.
Right? So the rook polynomial for x b prime. Well, we'll hold it. That's just going to be the same count as before, isn't it?
I think so.
Yeah. So for this one, so let me just, we don't even need to, okay. So let's just remark that for, what did we just do? 5V? For the 5V match, what's going on? We get the same count. Oops. We get the same count
Right.
as what? As 1V above,
Yes.
right? Uh, and what was the other one? 2V? Was that it?
Yep.
Okay, so what about 2V? Well, that's a little bit more interesting, I guess. So 2V, well, let's think about this. So that means I would, let me erase this. Oh, man. Okay. Do I have everything in here?
You dropped the one X on the inverted
Oh,
L.
wait a minute.
Oh wait, no, if you're
I dropped an entire
at least
row.
initially, yes.
Okay. Okay. So then I go 2V, yeah?
Mm-hmm.
So that would eliminate this column and this row. Okay. That's interesting. That's gone. And that's gone. So the rook polynomial for that board, I don't know, let's call this B prime prime. Okay.
Okay.
What's that going to be? Well, we can almost just stare at this for a minute and figure out the rook polynomials for the smaller boards. It's just going to be 1 plus 4x plus, what is it, 2x squared
Yeah.
times, oh man, that other one's easy. It's just times 1 plus 2x, right?
Right.
Okay. So what is that? Let me write it down here. So that's going to be 1 plus, so how many x are we going to have?
6.
Yeah. Okay. How many x squared will we have?
10.
Yeah. Plus,
4x cubed.
okay, so we have it, right? Then you could just basically write down the number of configurations where that's true.
Yep.
Just,
And then just add those together and divide by the original thing we found.
yep. That's
Awesome.
exactly right. Yeah.
Okay. Yeah, that makes a lot of sense. I didn't think of ruling out rows and columns.
Yeah, it just kind of makes
For
little subproblems that are easier to handle. That's cool.
Mhm. Yeah.
Hey, that was fun.
Thank you for your help on that one.
Yeah.
If you have a little bit more time, I'd like to spend just a few minutes talking about problem 7,
Sure.
also in 8.3. I did work through this one, and I got the right answer after working through it, but I did have a few more conceptual questions.
Okay, can you read it to me?
Yeah. It's a computer dating service wants to match 4 women with one each of 5 men, and then it lists a series of incompatible pairings, and then
So 4
asks
women and 5 men?
yes, and then asks how many matches of the 4 women are there.
So basically,
So it's kind of like the dwarves
get
problem,
left out, right?
right? But as I was working through it, I don't know if you can see this. Let me see if I can show you my finished board again. It's the one by my index finger.
Here, let me
After I
see. I'll
rearranged
make this a little
everything.
bit bigger so I can see.
Yeah, right up here. There's my finished board.
Okay, so there's 4. Okay, okay, okay. Oh, is there only 4? Wait. How many men are there?
5.
Okay, so let me mark this down, or let me write this down. So it's M3, M5, M1, M2, M4. And the women you have numbered 1, 3, 4, 2.
Yeah.
Okay, so let me quickly kind of sketch this thing. Yeah, all right. So that, and then you have like a little W at the bottom there. That's kind of interesting. There we go.
Did you get it?
Yep, I think so.
Okay.
So let me see. I'll put this back up here now. Oh wait, I have to unpin your face. Okay, here we go. Okay, so boop, boop, boop. Okay, so I have it here. Like that?
Yes. Okay. So one of my big questions was just looking at this board initially. I ended up not using the theorem 3 technique with the BS and the BS star to find the number of ways of the subboard for that pattern in the lower right hand corner,
Yeah.
because it seems simple enough that I could just do it normally. But I was just wondering, more generally applied to all these kinds of problems, is there a certain clear point where I should switch from trying to count this like we have been versus using that technique and breaking it up into further subboards?
I mean, so when you did this, why were you trying to use um you were trying to use in like the stars from 8.2 or what did you say you were trying to use?
Sorry, I was trying to use the method of further or breaking up an unbreakable subboard using that
Oh, well, I
technique.
don't know that I would. Oh, like the S and the BS.
Yes, so you'd rule out that cell M24.
Yeah, I mean you could do that. Although this is probably easy enough that
Right, and that's what I realized. I started to do it, and I was thinking, this is way too much work. So I was just wondering, is there kind of a
yeah.
rule of thumb you use for when you decide, okay, I'm going to switch from trying to do this normally to that method?
Well, I mean 3 rows and three like this only has 3 rows and 3 columns in it. So I mean it seems pretty straightforward. if you have like 3 rows or less to deal with, that seems reasonable. But once you get to like 4, that starts to get a little bit more hairy. You know what I'm saying?
Okay, so about 3 rows or columns.
Yeah, I mean, if 3 rows or columns, you can basically just do it, right? Without having to break it down. It's just nice to have that technique in your back pocket in the event that you have something that is fairly complicated.
Okay, that makes sense. And then my only other question for you, and this is kind of going back to that random question I threw in as you were solving the last problem, is once, or I guess I can give you the rook polynomial for the entire thing.
Oh,
And
what is the rook polynomial?
it's 1 plus 7x plus 16x squared plus
Okay.
13x.
Okay, so let me hang on. So let me see if I just want to see it for myself. So 1,
Sure.
5, 10. Okay, got it. 10, and then how many ways to replace 2 on that? So okay, 1, 2, 3, 4, 5. Yep, I see that it's 16.
Okay. And then it's, let's see, wait, 13x cubed.
Let me see. So yeah,
And then 2x to the 4th.
yes, I believe it.
Okay. So when I used one of the theorems in the book and just added those up and multiplied by those factors of the, what's it called? Factorials, I guess. This is what I got, and I liked using this summation notation, if you can see that.
Let me see. Oh man, how do I expand this thing?
Alternatively, it's a little cleaner. I can just show you when.
I'm trying to like make this. I'm trying to make it big so I can see you. Hang on.
Okay.
Okay, can you do that again?
Yes.
Okay, I just made it bigger.
It's at the very bottom there.
Well, so this is where I kind of have a problem with you using factorials because how many, okay, so like it's different. Like since you don't have the same number of rows as columns, this is one of those situations where, uh, okay, so like what's the total number of assignments here? Like if I didn't have these restrictions.
Total number of assignments.
So how many options would the first, if the first lady didn't have any qualms about any of these guys, how many options would she have for which man she could pick?
Is the entire answer 4.5?
Well, so okay, so like the total number of assignments with no restrictions at all would be 5 for the first column times 4 times 3 times 2. So it's kind of coincidence that you ended up getting it right, even though you wrote 5 factorial.
Okay.
Because there's less rows, there's less columns than rows here. Does that make sense?
Yes.
So it's really 5 times 4 times 3 times 2. Okay. And then you say, you take away all those that have one bad square. So it'd be minus 7 times, 4 times 3 times 2. Do you see? They're not really. I mean, they are factorials, but they're not, because you're kind of stopping the product before the 1. Does that make sense?
Yes. So I need to be more careful when I find that initial number. And then as I go through the terms, and does it still tick down by 1 every time on the factorial part?
Yes. Yeah.
Okay.
But like you would have been exposed if there would have been only 3 columns. You know what I'm saying? Because you would have written factorials, and that wouldn't have been right. You would have had to go like 5 times 4 times 3 for the total number of ways that you could assign things with no restrictions. Then you would have to take away the ones where there was 1 bad square, etc. So the answer is technically 5 put 4. That's the total number of assignments if there were no restrictions at all. And then you take away all the ones that have, so it would be 7 times 4 put 3.
Okay, and then that pattern would continue.
And then plus, so what would the next one be?
Actually, Dr. Hammett, I probably should go because I'd like to catch this live chapel that starts in a couple minutes.
Oh, yeah.
But sorry, I kind of threw you right into that middle of that problem when we didn't really have enough time to cover it.
Yeah, sure.
I think this is enough that I can kind of see what I should be doing.
Okay, but yeah, you can kind of see, like, the only thing that I'm saying here is that it is 5 factorial numerically, but technically the counting would have been wrong if you would have only had 3 columns. Yeah.
Okay.
Yeah.
That
Okay.
makes sense. Thank you very much for your help this morning.
Yep. All right. See ya.
See ya.